Okay. Yeah. So got that recording in case you want to access this later. Let me just set something up here. Yeah. And so, and if at any point you have questions, you can either I think there's like a little button you can like raise your hand. You guys see how to do that? I think on your yeah, somewhere on your settings you can do something like raise your hand, or you can just unmute your audio and pipe in with a question. Yeah, Kira's given the thumbs up. I see you there, Kira. Or you can send in a just a chat. You can send your question in via the chat. Taylor's giving the high five, maybe.
Hey.
Or was that the Michaela's there? Morning.
Good morning.
Yeah. Was that a question, Kayla, or you just showing you know how to do it?
Just showing I know how to do it. No question. Thank you.
Okay. Cool. And you might notice that there's two of me on there. That's because I have my iPad connected to the meeting as well in case I need to share my iPad screen. So that's why that's on there. So just one thing just to remember real quick. The exam will be a synchronous session. That doesn't mean that we're gonna be on Zoom. Where we're not gonna be on Zoom, but you'll be on. The exam will open up at 1:45 during our normal class time on Friday, and you'll have the normal amount of time to take that. If you have extended time permissions, then that'll be set into Canvas for you already to give you that extra time to take it. So that'll be all set up, but you do need to log in ahead of time and make sure you're all ready to go on Canvas, and the honor lock will be used. And if you haven't done honor lock for a little while, you may just want to hop on there and retake that practice quiz, or just make sure your computer's ready to go. Okay. So and obviously if there's any issues, you can just directly email me, or I probably probably just email me, or if you're having like technical issues with honor lock, then you can just use their chat right there, and they're responding really quickly to that. Kira is asking the question, just to clarify, I thought you said there were Zooms for exams and TBLs. Yeah, so we don't necessarily need to Zoom for the exam part because that's just going to be on Canvas. I just said that the exams are synchronous, which just means you're all taking it at the same time. You're not it wouldn't actually work to do the Zoom with the exam because Zoom takes your webcam, and so does the honor lock. So you can't really do both webcams at the same time. But they are synchronous, so everybody's taking the exam together. Does that make sense, Kara?
Yeah, thank you.
Yeah, you're welcome. Okay, cool. Well, we can just start out with any questions that anybody has. If people want to start throwing out questions about the material, again, either via the chat or just pipe in with a question.
Can we go over the lymphatic system, specifically with the conditions like ankle frames, hypertension?
Yeah, for sure. And are you thinking just go right to that table at the end of the lymphatic system notes?
Mm-hmm.
Yeah. Okay. Yeah. Why don't we do that? And I'll probably just do that by sharing my screen on the iPad. Probably the easiest way to do that. Let me just pull up those notes real quick. Hold on one sec.
Mute, can I can mute it. What do you need?
Okay, I think I'm figuring it out here. Hmm. All right, that is not working for me to share my screen with the iPad. Worked before, sorry about that. All right, well, I think we'll just talk through it then. And actually, I'll pull up that the image that I sent you guys that showed the lymphatic system. Okay, so let's go right to, all right, can you guys see my screen here? Looks like it, yeah, cool, okay. So the bottom line here with understanding edema, and really what I want you to understand for each of these conditions is really what kind of change we see in the osmotic pressure and the hydrostatic pressure. Okay, and we have to think about that in terms of, is that change happening in the blood vessels or in the interstitial space? Okay, and so we have to think about those two different spaces every time with one of these. So if we start with an ankle sprain, the underlying problem is the fact that there was damaged tissue there, right? So there's damaged cells, there was damaged blood vessels. Both of those things, when they were damaged, they dumped stuff into the interstitial space, right? They dumped cells, proteins, cell contents. All of those things lead to extra stuff in the interstitial space, which is really the equivalent of more solute out in the interstitial space. Okay, but then we get to the point where those blood vessels are healed. There's no more cells that are breaking, but there's still extra stuff in the interstitial space. The blood vessels at that point are kind of back to normal. Okay, but there's still extra stuff in the interstitial space, and that's why swelling is still there. So when we talk about the hydrostatic, so the underlying problem is that extra solute in the interstitial space from all of those damaged tissues. Okay, if we go over to hydrostatic pressure in the vessels, there should really be no change in that. The blood vessels are back to normal at this point, so there's really no change there. We go to osmotic pressure in the vessels. Okay, that's normal. Okay, there's really no change there. But if we think about osmotic pressure in the blood vessels relative to osmotic pressure in the interstitial space, then probably what I would write here would be that this osmotic pressure in the vessels is normal, but it's much lower than it normally is compared to the interstitial space, right? So there's a lot of extra osmotic pressure in the interstitial space. So that makes this osmotic pressure in the blood vessels relatively lower than it normally is compared to the interstitial space. So then when we go over to fluid flow, we have fluid flowing out of the blood vessels, extra fluid flowing out of the blood vessels, into that interstitial space because the osmotic pressure in the interstitial space is high because of all that extra solute there. Okay, and that would lead to edema. Okay, so questions on that one before we keep moving on? I wish I could write it. That's better, but sorry, that's not working for me. Any questions on that one specifically, on the ankle sprain? Okay. All right. And I'm not actually seeing the chat window when I'm sharing my screen. So if you have a question, just do it verbally. Okay. Okay. All right. So hypertension is another one. So hypertension really just means high blood pressure, right? So the underlying problem is that high blood pressure, right? You would write that there. So what would our hydrostatic pressure in our blood vessels be? This one's simple because the hydrostatic pressure in the blood vessels is higher than normal, right? Because that's what hypertension is just higher than normal hydrostatic pressure in the blood vessels. Osmotic pressure in the blood vessels, that doesn't change. So now when our blood enters the capillaries, and let's run back real quick to the beginning of these notes, because that's with the exercise that we did in the capillaries right here. This is really what this all comes down to, right? So when we have high blood pressure, this hydrostatic pressure, instead of being 35, maybe is now 40 instead, right? If this is still 22, then we're going to have a stronger driving force to push water out of the blood vessel into the interstitial space because this difference is greater, right? Instead of being a 12 millimeter mercury difference, it's now a 17 millimeter mercury difference. And see, the osmotic pressure stays 22 all the way through to the other side, but it's just that the hydrostatic pressure is slowly dropping. But water only starts coming back in when the hydrostatic pressure becomes lower than the osmotic pressure. And so if it started higher, then the water wouldn't start coming back in until later on, right? Here it shows it coming back in about halfway through. But in the case of high hydrostatic pressure with high blood pressure, that wouldn't start happening until a little bit later on. Okay, so that's the high blood pressure one, or hypertension. Yeah, so questions on that one? Let me go ahead and zoom to the end, back to that table. Oops. Okay, so any questions on the first two, on the ankle sprain or the hypertension one?
I have a question about the hypertension one.
Yeah, go ahead, Trey.
So can you repeat one more time? I was following along, but I missed the part where you said why it would be an edema then for the hypertension.
Okay, yeah, so it's just because, so let's go back to this, this other slide here. So this would be kind of the normal situation where we have 35 and 22 at the beginning. At the end, the hydrostatic pressure has dropped to 15 because some fluid is left, but osmotic pressure is still 22. Okay, so in the beginning, since hydrostatic pressure is higher than osmotic pressure, water's flowing out, right? But then at some point, maybe right around here, as blood's making its way through, this hydrostatic pressure drops below 22, right? And as soon as it drops below 22, then water starts coming back the other direction, right? And so, so let's say that happens right in the middle of the capillary under normal conditions. We push out a certain amount all the way up until about the middle. Once this hydrostatic pressure drops below osmotic pressure, water starts coming back, right? So we recapture a lot of that water. If we look right here, this is where it talked about we push out 20 liters of fluid a day, but then we pull back 17, right? And then that 3 liters that we don't pull back is what it can be handled by the lymphatic system to pick up that extra 3 liters. So we don't end up getting any edema in that case. But if now we have this situation where this hydrostatic pressure is so much higher because of high blood pressure, then it's going to take it. We might not get to the point where hydrostatic pressure drops below osmotic pressure until maybe we're 3/4 of the way through the capillary instead of half of the way through. So instead of pushing out 20 liters of fluid, we probably push out 25, right? But we're still only able to, and then instead of pulling back 17, maybe we're only pulling back 15, right? Because we have less time where the hydrostatic pressure is lower than the osmotic pressure. And then the lymphatic capillaries are only able to pick up about 3 liters per day. Maybe they can get a little bit more than that, but pretty much we put too much fluid out here, more fluid than the lymphatic system can pick up in a day. And so that just results in having extra fluid in that interstitial space. Does that make sense, Trey? And
Yeah,
others? Good. Okay. All right. Other questions on those first two?
So on the chart, though, the osmotic pressure doesn't change. It's just the hydrostatic is higher than normal.
For hypertension, yes.
For hypertension, yeah. And then for the ankle sprain, the osmotic pressure is higher or lower?
So for the ankle sprain, osmotic pressure in the blood vessel in here doesn't change.
Okay.
But the one thing we don't really even have on this image is osmotic pressure out here in the interstitial space, right? Because that's going to really affect this as well, because the two forces that are driving fluid out are hydrostatic pressure in the blood vessel and osmotic pressure in the interstitial space, right? Those are the two things that would be drawing water out of the vessel into the interstitial space. So we're really thinking about the hydrostatic pressure here, but also if we have a lot of extra osmotic pressure out here, that helps this hydrostatic pressure pull fluid out, right? And that's pretty much what's happening in the case of an ankle sprain, where we've got extra osmotic pressure out here that's helping to pull more fluid out. And it would do the same thing where we would be losing more water than we're pulling back. And so more would just end up out here. Because this osmotic pressure here, the part of the equation that's not shown on here, is this osmotic pressure in the capillary has to be greater than the osmotic pressure out here to pull fluid back, right? And so when we have really high osmotic pressure out here, it's a lot harder to pull fluid back into the blood vessel on this end of the capillary. And that's the case with the ankle sprain.
Okay, thank you.
Yeah, for sure. Other questions on those first two? So we have a real clear distinction between the ankle sprain one is an osmotic pressure issue, and the hypertension is a hydrostatic pressure issue. Okay, but then if we go to the other ones, Kwashiorkor, which is that problem, the underlying problem there is low protein intake in the diet. Right, so low protein intake in the diet means that you're not able to make plasma proteins. So you don't have the right components to make enough plasma proteins in the blood. So that doesn't really change hydrostatic pressure in the blood vessels. That would be pretty much the same. But now, since we have less plasma proteins in the blood vessels, we have decreased osmotic pressure in the blood vessels. So let's go back to that other slide. It really all connects to that. So now with Kwashiorkor, we still have the 35 millimeters of mercury here, but instead of 22, maybe we've only got 15 millimeters of mercury of osmotic pressure here because we don't have plasma proteins, right? So we have a 20 millimeter of mercury difference instead of a 12. Is that right? 12? No. What is it? 13. Yeah. 13 millimeter mercury difference. 35 minus 22 would be the 13. But if this is only 15, then we've got a 20 millimeter mercury difference. So it takes a lot longer for the hydrostatic pressure to get all the way below 15, right? That might happen all the way down here. So again, we're pushing water out for longer in the capillary bed and pulling water back in for less amount of time. So it results in more fluid staying out here in the interstitial space, probably more than the lymphatic system can pick up. So we result in some swelling. Questions on that one?
I have a question about, so is the reason why the hydrostatic pressure, or sorry, the osmotic pressure is lower, like you said, 15, is it because like there's, since they don't have the enough plasma proteins, is it just because that there's not as much stuff inside of the vessels?
Yeah, exactly. There's less solute in the vessels. And
Okay.
the main solute that contributes to osmotic pressure in blood vessels is those plasma proteins. Even though typically we've thought of it when we think about other things, we think about like salts and stuff like that. They do contribute to osmotic pressure, but the biggest contributors to osmotic pressure are really proteins. Yeah. All right. Other questions on that one? Okay. And the last one is actually involves the most components, really, because liver failure has two separate underlying problems. Number one is we have damage to the liver. So that means some of the liver cells, or also known as hepatocytes, are damaged. And so the blood vessels that are feeding into the liver are meeting resistance because when your liver cells die, they're replaced with scar tissue. And so pretty much blood vessels are being sent into this area that doesn't have smooth flowing blood anymore. It has a scarred up liver. And so that results in high blood pressure in the liver. Okay, because those blood vessels are meeting resistance because they're going through the scar tissue, that results in high blood pressure in the liver. Okay, so that's underlying problem number one, is we got high blood pressure in the liver. Okay, and then underlying problem number two goes back to the same thing with kwashiorkor, where the liver is responsible for making those plasma proteins. Okay, so if the liver is supposed to be making plasma proteins, but a lot of the liver cells are dead, then we just don't have the ability to make the same level of plasma proteins that we normally would. So we also have low osmotic pressure in the blood because of lack of plasma proteins. Okay, so underlying problem number one is high blood pressure in the liver. And underlying problem number two was not making plasma proteins anymore. Okay, so then when we go to here, we go to the hydrostatic pressure in the blood vessels. That's going to be high because of that scar tissue. Then what about osmotic pressure in the vessels? That's going to be low because of our lack of plasma proteins. And so again, fluid flow with all of these, fluid is flowing out of blood vessels into the interstitial space. But then let's go back to our image up here to connect this one. So in all of the other ones, we just changed one of the things. We just changed either hydrostatic pressure or osmotic pressure. In this case, we're changing both, right? We have higher osmotic pressure. So let's say this moves up to 40, and we have lower osmotic pressure. Let's say that moves down to 15, right? So now we have the biggest difference yet we've had between these two numbers. So that means we're pushing fluid out longer and more, and we're pulling fluid back less and less amount of time and just less total volume of fluid. So that results in lots of extra swelling out there in the interstitial space. So that can happen right in the abdomen in liver failure patients, where you see that huge pot belly sticking out, which is known as ascites. So that's edema right there in the abdomen that started in the liver. Okay, questions on that one or any of those other ones? Okay, we good on those? All right, so that's a great question for sure. So what else? What else we got? I'll go back to the chat window so I can see that. All right.
I had a question
Yeah.
on the adaptive immune system.
Uh-huh.
And I'm just a little confused. So the antigen presenting cells,
Hmm.
like those cells, they're not bad, right? They're just carrying the antigen, which is bad.
Yeah, they're not bad at all. They are very helpful because they're the ones actually going out and finding the antigen. Because
Okay.
remember, those lymphocytes, our lymphocytes are our B cells and T cells. Those guys are found in the lymphatic system. That's why they're called lymphocytes. So they're kind of buried, those B cells and T cells are kind of buried deep inside of those lymph nodes most of the time. So they don't really have a good chance of interacting with things that just get into your body. So we need these kind of mobile watchmen to go out and find what's interacting with the outskirts of our body. And then those cells can bring the invaders back and show kind of the headquarters, which are the B cells and T cells, right? So yeah, our dendritic cells, our macrophages, those are our two most common antigen presenting cells. And they're going to pick up the antigen first as soon as it enters the body. And then they're going to end up back in the lymphatic system, show what that antigen looks like to our helper T cell, right? And then that's going to activate both the B cells and the T cells to design weapons or antibodies or cytotoxic T cells that'll be specifically designed to just destroy that one antigen. That makes sense, Jamie?
Yes, thank you.
Cool.
And just to clarify, so
Yeah.
when the APC cells bring back like the antigen,
Mhm.
do the APC cells die? Like, because one of the things for the cytotoxic T cells is the granzymes stimulate apoptosis or
Oh
whatever.
yeah, apoptosis. Yeah.
So do sometimes like the cells just die altogether to kill it?
No. Yeah. I mean, they could be killed by the antigen out in the periphery, but if they made their way back to the lymphocytes with the antigen, then they would have destroyed the bacteria or whatever it was, and then they just save kind of a piece of that. They don't have necessarily the whole bacteria; they have a little piece of it, and they're presenting that little piece of it to the lymphocytes. And then the part that you mentioned about the granzymes and the
Perforins.
perforin, there we go. The perforin, so yeah, let's go to that actually. Let me pull up that slide and let's walk through that because that's an important process here. Okay, so when we look at the adaptive immune system here, one of the key thing to understand here is first of all, the first step is that APC, or the antigen presenting cell, showing the antigen to a helper T cell. That's what activates the whole adaptive immune system. And there's two key connections that happen there. One connection between the two cells is the CD4 protein on the T cell binding to the MHC2 on the APC. That's a lot of mumbo jumbo. It sounds like a lot of different acronyms for sure, but CD4 is just a certain type of protein that T cells have. And then MHC2, remember, is that kind of like that law enforcement ID, the thing that would tell the helper T cell, all right, this guy is part of our team, right? This one is trying to help us out. And so that's the first interaction. And then that second interaction between the two cells is the T cell receptor, and that binds right to the antigen that the APC is presenting. Okay, and then we see that here, right? We see all of this where we have the APC right here. It had already ingested this antigen, processed it, and put a little piece of it out here, and it's being held right here, and it's connected to the MHC2, and so now the antigen connects with the T cell receptor. The CD4 protein connects with the MHC2, so we see those two connections. Once those two connections happen, the T cell activates, releases all these cytokines, and then activates a bunch of other T cells that are around. Okay, so there's other T cells around the area. These interleukins will stimulate those to start proliferating, start dividing, making more and more T cells. Some of those T cells become memory T cells, so we're ready to get that same antigen next time it comes in. But a lot of them become cytotoxic T cells. And the cytotoxic T cells are the ones that are actually going to go and destroy. They're going to go look for this antigen now. And that's kind of the next step. And this is the part you were talking about, Jamie, where we have a T cell right here. So a cytotoxic T cell, that this is one that's already been activated by that helper T cell. Now it's going to go find a cell of the body that's infected with that same antigen. Right? So it finds one of your normal body cells. And when that body cell is infected with that antigen, it's going to present that antigen on its cell surface. So those T cells that are floating around looking for that antigen, they see a cell that says, hey, I've got this infection. It binds to that, ensures that it's the right one to kill, and then it releases these perforins, which poke holes in the cell, and then dumps in these granzymes, which cause the cell to destroy itself. And so really it's not destroying the antigen itself, but it's destroying the cells that are infected with the antigens, so they don't keep spreading. This is exactly what happens with viruses, right? Like the one that our whole world's dealing with right now is exactly how COVID-19, or how the coronavirus acts, is it takes over a cell's machinery and causes that cell to start reproducing itself over and over and over again. And then that cell just starts spewing a bunch of that coronavirus out into the rest of our body. All those little viruses get into the rest of our cells, start reproducing themselves that way. Okay, but any of those infected cells, if our immune system is trained against it, then those cytotoxic T cells are going to do their best to destroy all of those infected cells. So,
Thank you.
yeah, for sure. And then we might as well talk about the other one too. So the other level of immunity is the humoral response. So that was just that's known as the cellular response on the adaptive side, the one we just talked about. The second one is the humoral response, and this is what involves B cells. Okay, so that helper T cell, that same one that interacted with the APC and activated those cytotoxic T cells, the same interleukins it was releasing to activate those T cells. It also, hold on one sec. I think somebody just started vacuuming right outside my door. I'm going to ask them to take a break for a sec. Okay, I'm back. Yeah, so that same helper T cell that activated the adaptive, or activated those B cells or those T cells, now it's also going to activate B cells. Okay, and one key thing, B cells, when they get activated and they start releasing antibodies, then we call them plasma cells instead of B cells. Okay, and so this is that process, that same helper T cell that had activated the B cells is now going to release interleukins and activate this B cell here. Okay, we have two connections as well. We have the helper, the CD4 protein, again interacting with the MHC2, and we have the T cell receptor interacting with the antigen again. Okay, so this pretty much shows the B cell, here's what that antigen looks like, and make antibodies to destroy specifically that antigen. Right, and then this is the way that all those antigens can act to destroy the different things, this is the way the antibodies act to destroy the antigens. And this just kind of shows those different processes there. Questions on that side of it, or anything else about the adaptive immune system?
Yeah, I have a question.
Yeah, go ahead, Gracie.
Do the antibodies that the B cell just made, do they leave the B cell to go attack the antigen? How does that work?
Yeah, good question. So the antibodies, so we have this process of the B cell getting activated here by the helper T cell. This would most likely happen inside the lymphatic system, like inside of a lymph node. And then at that point, so there's a bunch of helper T cells activating literally thousands to millions of these B cells. As soon as it gets activated and gets trained to know how to make that right antibody, which happens quickly, then those B cells are going to make their way back into the bloodstream. So they get dumped back into the bloodstream out of the lymphatic system. As soon as they hit the bloodstream, now they just start spewing out antibodies like crazy. And like it says here, it's an incredible number. It's about 2,000 antibodies per second that they release. And they can do this for 4 to 5 days. So they're doing this all throughout the bloodstream.
Okay, thank you.
Yeah. And I think maybe somebody put a question on the chat. I mean, I can't see it from this view. Stop sharing. Okay. Let's see. Yes, Chriselle, I will go over the effects of local versus systemic blood flow in a sec. That's always one that, yeah, we'll definitely need some clarification on. Anything else on the immune system while we're here?
I have a question about like where everything's located.
Okay.
So, like, are these are the cells of the adaptive immune system mostly located inside of like the lymph nodes and like the lymphatic system, or do they also go into the bloodstream and like patrol through there?
Well, so you said of the adaptive system?
Yeah.
Are you just thinking like all of them?
Just in general, like the immune like cells.
Yeah, so they're everywhere for sure. But the T cells and B cells specifically are called lymphocytes because for the most part they're in the lymphatic system. But then when they become active and they go out to fight infection, when the cytotoxic T cells become active and the B cells become plasma cells, then they get into the bloodstream and then they're circulating around doing their job. But they're also not even just in the bloodstream, they get into the tissues as well. So when a cell or when some tissue has some damage to it, the blood vessels around that tissue will express little proteins that are pretty much like little flags that call the immune system in. So if a macrophage is going kind of rolling by a blood vessel that has some damage underneath it, it'll have a little protein that causes that macrophage to stick there. That'll call the macrophage into the tissue, and then the macrophage can do its work there. So in general, those cells of the innate immune system we talked about, like macrophages, the mast cells, the neutrophils, the dendritic cells, all those and even the natural killer cells. Those types of cells are kind of everywhere all the time. They're throughout the tissues, they're in the blood, but then specifically those lymphocytes like B cells and T cells, they'll spend most of the time in the lymphatic system, but then when they get activated to come out and do their work, then they're in the blood and the tissues. Does that answer it, Trey?
Yeah, that makes sense. Thank you.
Cool. All right. Okay, we got a question on the chat here. Can antibodies do all the actions in plano or just certain ones? Do specific antibodies have specific actions? They can all do all of those actions. Yeah, so all those different things are common things that antibodies do. The only caveat, I guess I would say for that would be that some of those actions apply to specific types of antigens. For example, the precipitation one, that only happens to really small antigens. Okay, precipitation wouldn't happen to a large bacteria because they're too big. Precipitation only occurs when we take small things that are dissolved into the water and then pull them out of that. So it wouldn't happen in a large one. So that's kind of one example of where it's not always, not all of them would act in the same way. Okay. Anything else on the immune system before we talk about blood pressure control a little bit?
Could you go over the vasodilation and vasoconstriction in regards to hypersensitivities of type 1?
Oh yeah, for sure. So yeah, let's go. So that's at the very end of the adaptive immune system notes. And let me share my screen again here. Yeah, so we have these different hypersensitivities of the immune system. And here. So this is all driven by mast cells, and mast cells are commonly found in the tissues. So they might just be kind of in the tissues right underneath your skin, and maybe you interact with something, or let's think about it more in terms of like a mucous membrane. They might be found right under the mucous membranes in your nose and in your throat. And so you breathe in some dust or some cat fur, cat dander, and that sticks to that mucous membrane, absorbs down in to the tissues, and then there's a mast cell right there, and it picks up that. If you happen to be allergic to whatever that is, whether it was dust or cat dander, then that mast cell gets activated by that, and it releases histamine. And histamine automatically causes vasodilation, so that opens up blood vessels, so we get more blood flow to that area. And then it also causes smooth muscle contraction in your bronchioles, in your lungs, right? So it opens up blood vessels, but it constricts your airways, okay? And then it also causes mucus production. That's why we get runny nose and have to, cough stuff up, okay? So that's what histamine does. If we have a drastic reaction to that happens all over our body all at the same time by one of those allergens getting into our bloodstream, like a peanut allergy or something like that, then we get systemic vasodilation, which is bad, right? That drastically drops your blood pressure, and we get all of those bronchioles constricting. So this is what happens when someone's having this allergic attack or anaphylactic shock. All their blood vessels open up, so their blood pressure drops really fast, and then their airways close up, so they have a really hard time breathing, right? So you guys all remember from our autonomic nervous system notes that the sympathetic nervous system does the exact opposite of that, right? So the effects of the sympathetic nervous system on our blood vessels are to vasoconstrict, right? And then the effects of the sympathetic nervous system on our lungs are to open up the airways or dilate the airways, right? Which is the exact opposite of what histamine does. So that's why people that have severe peanut allergies and bee sting allergies have to carry EpiPens with them. So if you end up in this situation where you get a dangerous drop in blood pressure or massively constricted airways, give yourself that EpiPen injection that sends a large amount of epinephrine through your bloodstream, just like would happen from your adrenal medulla if you're stressed out, and all your blood vessels constrict, all of your airways open up, right? So it does the exact opposite of the allergy. Okay, that answer your question, Kayla?
Yes, thank you.
Cool, yeah. All right, and then the really interesting one I think is the type 4 hypersensitivities like poison oak and poison ivy. Those things are oils that absorb through your skin, and they don't have anything to do with the mast cells, but what they do is they actually attach to those MHC1 proteins, the ones that the immune system is supposed to be able to look at and tell that a cell is part of the body. Those things actually attach to those proteins and mess them up in a way to where the immune system doesn't recognize them anymore. So that next time the immune system, specifically T cells, interact with those cells, the T cells destroy your own cells because they don't recognize them anymore. And that's the way that those type 4 hypersensitivities happen. Okay, any other immune system questions before I talk about blood pressure control?
Yeah, I have a question.
Okay.
Why does it take 1 to 3 days for it to appear?
Yeah, good question. It has to do with that fact that our lymphocytes, our T cells, aren't they're not all the way, or they're not out in the tissues normally, right? So they're not typically out there in the tissues. So it takes a little while for a mast cell to, some type of APC to recognize that this cell is an invader, get back to the lymphatic system, show that lymphatic system, or show those T cells the new antigen, which is really just your cell, but it's a messed up version of your cell, and then it takes a while for those T cells to make their way back to that infected area, not infected, but the area that was affected by this. And so, yeah, it's really just that whole process of antigen presentation and then the T cells getting back to that area.
Thank you.
Yeah. Other immune system questions? Okay, let's talk a little bit about blood pressure control in the time that we have left. I'm going to send out the invitation to this again right after our meeting, but there's also a review session, tutorial center review session today at 4:30, and I'll send out the Zoom link for that as well. But this one, let's see, I think we're going till just about 10:30 today, and I have some more advising meetings right after that. So, but let me pull up the notes on blood flow and pressure, which I've gotten a lot of questions about via email and a couple questions here. So probably the part that we need the most help on is this difference between local and systemic changes in blood pressure and blood flow. Okay, so when we think about, so this is kind of the overview of this. Local changes look at pretty much changes just directly to one little area. And we really don't have to worry too much about this myogenic one. We talk more about the metabolic one. And the bottom line is with the metabolic one, anything that is a result of increased metabolism leads to dilation, because that'll bring more blood to that area. And anything that's a result of decreased metabolism will lead to constriction and less blood to that area. Okay, and that's just right there in that specific area. That's a local response. Whereas the sympathetic nervous system is different. That is where we're talking about the extrinsic or systemic response. And so the higher activation we have of the sympathetic nervous system, the more systemic vasoconstriction we have. Okay, so probably the best place to go would be this image right here that kind of summarizes it. And one thing to help you understand this image is that up here, these two boxes are both the vasodilation parts. And then these two boxes down here are both the vasoconstriction parts. Okay, the left side, these greenish boxes, are our local control. Okay, and then the blue boxes are the systemic control. Okay, so again, the things that are going to cause vasodilation on a local level are metabolic things that are connected to more metabolism. So just by a show of your thumbs there, we're going to go up for more metabolism, down for less metabolism. Let's do it together here, okay? So when we talk about oxygen levels in the blood, do we think that higher oxygen levels in the blood would be connected to more metabolism or less metabolism? So higher oxygen levels, do we think that would be less or more metabolism? Okay, I see most of you saying, let me see if I can see a few more of you. There we go. Yeah, so most of you are saying down, or you're saying less metabolism. That's right. If we have more oxygen, that means we're not using it, right? So then the next question is, would that cause vasoconstriction or vasodilation? And so hold up a 1 for vasodilation and a 2 for vasoconstriction. Okay. So more oxygen, do we want to vasoconstrict or vasodilate? So 2 for constriction, 1 for dilation. Okay. So yeah, we're getting more towards the 2, but there's a few 1s out there too, right? So that's a key point. If we're doing less metabolism and higher oxygen levels are a sign of that, then we don't need to send blood there, right? We don't need to send blood there because it's not an active area. So we're going to vasoconstrict. Okay, so that would be vasoconstriction. So look at these metabolic changes. So the ones that are vasoconstrictors are high oxygen, right? Increased oxygen. Ones that are vasodilators would be decreased oxygen, because that would be a sign of more metabolism, because we're using up that oxygen in our oxidative system, right? And then the rest of them are kind of byproducts of doing a lot of metabolism, right? So high CO2, high hydrogen, high potassium, those things are all associated with doing a lot of metabolism. So if we have high levels of those 3, that means we're doing a lot of metabolism. We need to get more oxygen there. So let's open up the blood vessels, let's vasodilate. If we have low levels of those 3, that means we're not doing as much metabolism. So we need to send less blood there, so we vasoconstrict. Okay, so those are the local mechanisms. Questions on those so far? Okay, so at that same, then if we look at the blue boxes here on the right, we have the systemic ones, okay? And really the only systemic one that we're talking about is the sympathetic nervous system. And so when we're stressed out on a systemic level, let's say when we're exercising, and again, we can do this by a show of your thumbs, would we want more sympathetic nervous system activity or less? So more would be thumbs up, less would be thumbs down. When we're exercising or when we're stressed out, do we want more sympathetic or less sympathetic? Let me see those thumbs. Okay. Yeah, so we want more sympathetic. We're a little bit mixed on that, on the thumbs there. We got some up, some down. Okay. So we want high blood pressure when we're stressed out. Okay. We want high blood pressure when we're stressed out, so we can move blood quickly. We want to be able to get blood all over the body rapidly, and the only way to do that is to have high blood pressure. Okay, so that would be systemic vasoconstriction would cause that, right? So we have higher sympathetic tone, which means just higher sympathetic activation. That leads to vasoconstriction. If we have lower sympathetic activation, that leads to vasodilation. Okay, so let me just back up to one thing that can sometimes be confusing, which is these chemoreceptor reflexes. Okay, these chemoreceptor reflexes show that high CO2 or high hydrogen stimulates the sympathetic nervous system. Okay, we didn't really talk about that right now. We just talked about the sympathetic nervous system. But don't let this confuse you, since CO2 and hydrogen are part of the local response. They also are what stimulates the sympathetic nervous system. Because when we said on this slide, sympathetic tone, increase or decrease, there's nothing that tells you what does that. So that slide back here on the chemoreceptors, that just tells you one of the things that does that, right? How do we stimulate the sympathetic nervous system? We can do that if we sense high levels of CO2 or hydrogen at these very important areas in the carotid arteries or in the aortic artery. So if we have high CO2 in our aortic artery, that means that we're doing a lot of metabolism through the whole body. So it'd be a good idea to raise blood pressure. Okay. Yeah, and if we have very low CO2 or low hydrogen, that means we're not doing much metabolism in the whole body. So it'd be a good idea to decrease blood pressure. We don't need high blood pressure in that situation. So let's decrease the stimulation of the sympathetic nervous system. But still, that's a systemic one, not a local one in that case. Okay, questions on that part? So the thing to come back to there is that these two things are working together, right? So the best example, I think, and the one I always think of because I study exercise physiology, is exercise, right? When we're exercising, let's say we're riding a bike, okay? We're riding a bike and we're using our quads a bunch, okay? And so we're using our quads, and those quadricep muscles are using a lot of oxygen, right? So around the muscles that are using a lot of oxygen, we'll have low oxygen. We'll also have high CO2, high hydrogen, high potassium, because those are associated with using that oxygen too. So right there locally at our quads, we're going to vasodilate, okay? So that's good. We get some more blood to our quads, but that wouldn't help us too much if we didn't also have high blood pressure to get blood to the quads, right? So then on a systemic level, that exercise is also very stressful for our body. It might lead to high CO2 a little bit up again in that carotid artery or in the aortic artery. And so we need that to activate our sympathetic nervous system down here so we can get systemic sympathetic tone, systemic vasoconstriction. So this is really what we need. We need to systemically vasoconstrict. So all of our blood vessels are small, so we got high blood pressure. And then in that one place that needs a lot of blood flow, which would look like this, it would have low oxygen, high CO2, high hydrogen. We need to vasodilate so we can get blood to that area rapidly. Okay, so it's that kind of contradiction of locally we're vasodilating in the area that we need the blood, and then systemically we're vasoconstricting so we can move blood fast. Okay, questions on that? Okay, guys. Any other questions you wanna ask at this point?
I have a question about the exam.
Okay.
Are we going to be allowed to use scratch paper, or will that be like problematic?
Yeah, no, you definitely can. Yeah. And yeah, it's a good question. So probably what I'll ask you to do is just when there's going to be a thing that prompts you to show your ID card when you take the exam. I think that's probably how you'll find with other classes too. At that point, you can kind of just show, here's my one piece of paper I'm going to use. It should be blank at that point, and then you can write down things on it like you would during the test.
Okay. Thank you.
Yeah, good question. Okay. Anything else? Okay, guys. Well, it's good to see all of you. Thanks for showing up here this morning. And again, this is being recorded, so I'll go ahead and post this to YouTube with that same way we had before. It's an unlisted link, so it's not like anybody can find it. Only people with the link can find it. So that'll be there for you. Okay. Somebody says, if we have syllabi on the wall, do we need to remove them? Yeah, you wouldn't want things that could potentially be incriminating on the wall. But that's really cute that you have syllabi on your wall, Trey. That's pretty cool. All right. Okay. Good to see you guys, and have a great day. Feel free to email me questions if you have them, and I will post the video lecture video at some point for today, but I don't know if I'll get to that by today. I'm going to try, but it's not, the stuff on there isn't needed until exam 5 anyway. So it'll get posted by Friday for sure. So, all right, guys, have a good one, and we'll see you all soon.